histology. I'm sure that you have done the gross anatomy of the male reproductive system, so I'm not going to go into the gross anatomical aspects. We are only going to talk about the details about the histology of the male reproductive tract. So the major aim here is to look at some of the histological structures and some histophysiology of the male reproductive organs. We will learn the histology and histophysiology of the testes. We'll learn the histology and histophysiology of the genital ducts. And then we will go into some associated glands like the seminal vesicles, prostate, bulbourethral gland, and finally we will look at some of the histological aspects of penis. So we know that in the male reproductive system we have two testes which are important in the formation of the sperms, and synthesis and release of the sperms is also important in terms of the functions of the testes. It also releases an important hormone which is called the testosterone. So we will see from where the testosterone is coming in and how it is regulated. Then we are going to talk about the genital ducts, which take the sperms from the testes into the urethra. So we are going to talk about the internal duct system and the external duct system, which is important in terms of the transport of the sperms to the urethra. And then the associated glands, which include the seminal vesicles, the prostate, the bulbourethral gland, and finally the delivery of the semen to the female reproductive system through the penis. And so we are going to talk about the penis. So looking at the testes, they are present inside the scrotum, and they are, initially embryologically they develop in the abdomen, so in the posterior abdominal wall. So in front of them is basically the peritoneum. So when they descend down from the posterior abdominal wall and passing through the inguinal canal to the scrotum, they take part of the peritoneum in front of them, and that is called the tunica vaginalis. So tunica vaginalis is a part of the peritoneum which descends down with the testes as they descend during their embryological life from the posterior abdominal wall through the inguinal canal into the scrotum. Later on, this communication with the peritoneum closes, so you have just the tunica vaginalis covering the testes in front. And then outer to the tunica vaginalis there is a vascular covering which is called the tunica vascularis, and then there is a capsule, a thick capsule of the testes which is called the tunica albuginea. So what you are seeing here is the tunica albuginea, which is the capsule of the testes. And below this there would be a vascular connective tissue which is called the tunica vascularis, and then you have the peritoneal layer which is covering the front of the testes and the lateral part of the testes, which is called the tunica vaginalis. So there are three layers which are covering. The most external one is the tunica albuginea, then you have the tunica vascularis, and then you have the tunica vaginalis, which is basically the continuation, initially the continuation of the peritoneum, but later on it's an enclosed sac which covers the testes from the front and from the lateral side. The posterior aspect of the testes, the tunica albuginea, gets thickened, and this tunica albuginea, as it becomes thickened, it is going to send septas inside the testes, dividing the testes into lobules. So there would be testicular lobules. There are about 200, 250 lobules, and these lobules are formed by the septas, connective tissue septas, which come out from the thickening of the tunica albuginea posteriorly. This thickening of the tunica albuginea posteriorly is also called mediastinum testis, because this is the place from where the ducts are going to go in or come out, or the vessels are going to go in or come out. So this posterior aspect of the testes, where the tunica albuginea is going to become thickened, is called the mediastinum testis, and it is the place from where the ducts are going to come or go in or out, or the vessels are going to go in or come out. And from here you have the septas from the tunica albuginea, which are coming in and dividing the testes into several lobules. So testes are paired oval organs located in the scrotum. They develop retroperitoneally and carry the peritoneal outpoaching, which is called the tunica vaginalis. Tunica albuginea is an irregular, dense connective tissue which surrounds the testes, and it forms a capsule. Tunica vascularis is located immediately below the tunica albuginea and is the vascular layer of the capsule. Now, this is what you are seeing here. This is the tunica albuginea. It is sending septas in, and these septums are going to divide the testes into lobules, and within each lobule there are highly coiled tubes which are called the seminiferous tubules. There are about 3 to 4 very highly coiled tubes within each lobule, which are called the seminiferous tubules. So if you go back here and see here, this is a lobule of the testes, and within each lobule you can see these highly coiled tubes. There are about 3 to 4 of them in each lobule, and these highly coiled tubes are called the seminiferous tubule. So now this is a histological section, and what you are seeing here is this is a tunica albuginea. There is a septum which is coming in and dividing this into a lobule, and this is the cut section of the seminiferous tubule. So it's a highly coiled tube, and if you cut it, you will see, you know, these circles, where these circular things are basically the lumen of the seminiferous tubules. So, as I said, the posterior aspect of the tunica albuginea is thickened to form the mediastinum testes, and there are connective tissue septas which originate from the mediastinum testes. So to subdivide the testes into 250, pyramidal lobules, and within each lobule there are about 1 to 4 seminiferous tubules. There is richly vascularized and loose connective tissue which are derived from the tunica vascularis, which surrounds the seminiferous tubule, and within this loose connective tissue which surrounds the seminiferous tubule, you have the Leydig cells, which are important, or they are called interstitial cells of Leydig, and they are important because they secrete a hormone which is called the testosterone. So testosterone is secreted by the interstitial cells of Leydig, which are present in the connective tissue around the seminiferous tubule. Seminiferous tubules are important because they are the ones which are going to give rise to the spermatozoa. So the development, there are 2 types of cells in the seminiferous tubule. One is the spermatozoa series, and the other are the Sertoli cells, or the supporting cells of the seminiferous tubule. So there is, when I say spermatogenic series, it means that the cells in the seminiferous tubule are at different level of maturity. So they start from spermatogonia, that means the most immature type of cells, and then they slowly mature into spermatids at the apex of the seminiferous tubule, and then the spermatids are going to differentiate into a mature sperm through a process of spermiogenesis, which we are going to talk about a little bit later. But you need to understand that within a seminiferous tubule, you have several generations from immature sperms to all the way to mature sperms, which are there, and also in between, separating them, are these cells which are called the Sertoli cells, which are supporting this differentiation. Okay, so within the seminiferous tubule, there are two types of cells: the cells of the spermatogenic series, which include immature to mature cells, and the other type of cells are in between them, which are the supporting cells. They are called the Sertoli cells. So seminiferous tubules, or the seminiferous epithelium of these produce spermatozoa. Spermatozoa enter the tubuli recti, which are the terminal parts of the seminiferous tubule. So the terminal part, because seminiferous tubule is a coiled duct, at the terminal part it becomes straight. So these are called the tubuli recti. Tubuli recti enter into this meshwork, which is called the retitestis. And then from retitestis you have the efferent ductules, which go into the epididymis, and epididymis then opens into the vas deferens. Vas deferens joins the seminal vesicles to give rise to the ejaculatory ducts, and ejaculatory ducts opens into the urethra. So what we are going to focus on first is basically the testes. We are going to look at the structure of the testes first. Then we are going to go to the straight tubules, then the retitestes, then the efferent ductules, then epididymis, and then to the vas deferens. So let's start to talk about these seminiferous tubules first, which are 1 to 4 within each lobule of the testes. They are about 30 to 70 centimeter long. So you can imagine that if something is 30 to 70 centimeter long, it's about 2 feet long, but it's coiled. So it's highly coiled, and the diameter of this tube is 150 to 250 micrometers. There are about total of 1,000 seminiferous tubules in two testes. So if you count the total number of seminiferous tubules, about 1,500 each in each testis. The tunica propria, which is the connective tissue layer surrounding the seminiferous tubules, make the wall of the seminiferous tubule. Then there is a basal lamina, which separates the epithelium of the seminiferous tubules from the tunica propria. So there is tunica propria, basal lamina, and then you have the epithelium of the seminiferous tubule. So if you are looking at this is a seminiferous tubule. There is tunica propria on the outer side, then there is basal lamina, and this is the epithelium, and then in the center you can see the lumen. So this is the lumen, epithelium, basal lamina, and on the outer aspect you have the tunica propria. Tunica propria contains type 1 collagen bundles and housing several layers of the fibroblast, which are not actually fibroblasts, they are called myoid cells. These myoid cells have the properties similar to the smooth muscles. So when they are going to contract, they are going to push the secretion of the seminiferous tubules towards the straight ducts and then towards the efferent ductules. So there is a couple of layers of fibroblast type of cells. They are called the myoid cells, and these myoid cells have the properties of smooth muscles. So when they contract, they are going to push the secretions and the sperms from the lumen of the seminiferous tubules towards the efferent ductules. Because remember, when the sperms are going to come out from the seminiferous tubule, they are still immotile. So they are not able to move because they are immotile, even though they have flagella, but they don't have the ability to move. They are immobile. They only get the ability to move when they reach the epididymis. So in epididymis, there is maturation of the sperm, which leads to their motility. Before they reach to the epididymis, they are immotile. So they need to be pushed. And how they are going to be pushed is because there is tunica propria, which has the myoid cells, which are specialized type of fibroblasts, and they are going to to contract and push the secretions of these seminiferous tubules into the lumen of the reproductive. There are spermatogenic cells and the Sertoli cells, which form the epithelium of the seminiferous tubule. So there are two types of cells which are going to form the epithelium of the seminiferous tubule. One are the spermatogenic series of the cells from immature to mature cells, and the other are the Sertoli cells. So if we look at the epithelium, you would start to find that you have this cell, which is more like a columnar cell, and this is resting on the basement membrane. It has a nucleus, mitochondria, and apical projections. So this cell is the Sertoli cell. And then you can see the cells which are from the spermatogenic series, starting from the spermatogonia, which is the most immature type of cell. And then you have the primary spermatocyte, the secondary spermatocyte, the spermatids, and these spermatids then get maturer while attached to the apical surface of the Sertoli cells. And then once they are mature, they are released into the lumen of the seminiferous tubule. They are taken into the efferent ductules. So the most immature cells which are present in the basal compartment are the spermatogonia. And these spermatogonia, they are going to divide by mitosis. So they are increasing in number by mitosis. There is no meiosis happening here. So the spermatogonia are the diploid cells, and they go multiplication by the process of mitosis. Now, you know that the sperm cells are actually haploid. So they are, the maturer sperm cells are haploid. So these spermatocytes are going to multiply by mitosis. They would start to become the primary spermatocytes. The primary spermatocytes are going to divide by meiosis, and they are going to give rise to the haploid cells, which are called the secondary spermatocytes. And as these cells are dividing, you can see that their cytoplasm is interconnected. You see, one clone of cell, the spermatogonia, as it is going to multiply, and then it is going to form the primary spermatocyte, it is connected to the clone of cells until it becomes the secondary spermatocyte and then the spermatid. So there is clonal, generation of the cells, and each cycle, from one stage to the other stage. For example, from spermatogonia to the primary spermatocyte, it takes about 16 days to happen. And there are about 4.5 cycles which are required to reach the final mature stage. So you can imagine that if each stage requires 16 days to go from one stage to the other stage, and you need 4.5 or 4.6 stages for the exact to reach the final spermatid stage or mature sperm stage, it means that you need about 84 days to get from the spermatogonia all the way to the mature stage. So if you want to use any drug therapy which is going to stimulate the spermatogenesis, the effects would be seen somewhere around 84 days, because you need these 4.5 stages, or 4. In some animals there are 6 stages. In humans there are 4.5 stages of development, and each stage required 16 days. So it would require about 84 days to reach the final mature stage of the sperm. And so if you want to induce spermatogenesis, and you are using a drug to induce spermatogenesis, it would require, to see the result, it would require about 84 days. Now, the other important thing is that within the Sertoli cells, which are mainly columnar cells, there are projections in the apical apical part of the Sertoli cells, and there are lateral projections also. And these lateral projections are going to connect the Sertoli cell on this side to the Sertoli cell on this side by tight junctions. So in between the Sertoli cells you have these spermatogenic series, and then you also have lateral projections from the Sertoli cells which are joined with each other by tight junctions. Now what is the reason why you need this lateral projections from the Sertoli cells which are going to join the other Sertoli cell? Yes, go ahead.
For the blood justice period.
Yes. So you would have two parts of the compartments of the seminiferous tubule. One is the basal compartment, and one would be the luminal compartment. So the basal compartment is where you would have the spermatogonia, and you have the primary spermatocyte. They are located in the basal compartment, and the cells in the luminal compartment will include the secondary spermatocyte and the spermatids. The reason why this is important, because you know that the spermatogonia are dividing by mitosis. So their DNA is similar to your any other cell. Their DNA and their proteins, the expression of the proteins on their cell surface is similar to any of your other cells. So, and the blood vessels are here near the basal part of the seminiferous tubule. So the immune cells are located here. So if there is an interaction between the proteins of the spermato, it will not induce an immune reaction. Why? Because the immune cells will see the similar proteins which are there in other cells. But the secondary spermatocytes and the spermatids, which divide by meiosis, and you know that within the meiosis there is crossing over also. So the proteins there in the secondary spermatocyte and the spermatids are different from the rest of your body. So if they get exposed to the blood vessels and the immune cells, it will result in an immune reaction against these cells. And then you would have, the cells would be destroyed. So actually, Sertoli cells, because of their lateral projections which are going to form the tight junctions with each other, they are dividing the basal compartment and the luminal compartment. The luminal compartment is not exposed to the immune cells, and that's why there is no immune reaction against your mature sperms. And in the basal compartment you have your cells which are dividing by mitosis, so they are similar to the cells which you have in the rest of the part of your body. So the primary spermatocyte, as we say, enter the first meiotic to form the secondary spermatocyte, which undergo the second meiotic division to give rise to the spermatids. So the secondary spermatocytes and the spermatids are the ones which are the haploid cells, while the primary spermatocytes and spermatogonia are the diploid cells. You can see it here again. This is the Sertoli cell. These are the spermatogonia. These are the primary spermatocytes. That's the secondary spermatocytes, the spermatids. You can see the myoid cells here. This is the basal lamina. So this is the histological structure of the seminiferous. Okay. So let's first talk about a little bit on the sperm also, and then we are going to go forwards with some regulation of the spermatogenesis also. So spermatids discard much of their cytoplasm and form a flagellum to become transformed into the spermatozoa, a process known as the spermatogenesis. And spermatozoa are long cells, about 65 micrometers, composed of head housing a nucleus and a tail, which accounts for the most of its length. The tail of the spermatozoa is divided into 4 regions: the neck, the middle piece, the principal piece, and the end piece. The plasma lemma of the head is continuous with the tail of the tail's plasma membrane. So if we are going to look at the parts of the adult sperm, you would find there is a head which is compressed, and on the top of the head there is an acrosomal cap, and that acrosomal cap consists of enzymes which are hyaluronidase, which are important in digesting glycoproteins when it is going to fertilize the egg. So the glycoproteins around the egg are digested by the enzymes secreted by the acrosomal cap, which is called the acrosomal reaction. So the head is compressed, it has a nucleus, and over the top of it is the, yes?
Where exactly the spermatozoa is the acrosomal cap?
Where is exactly is the?
Acrosomal cap.
I will show you in a minute. So on the top of the head, there is an acrosomal cap which is going to secrete several enzymes, including hyaluronidase, which is important in digesting glycoproteins around the egg. Then you have the neck part of the sperm, and the neck includes the centrioles, and it includes the coarse fibers. The coarse fibers are the ones which are going to initiate the tail of the sperm. So you have the centrioles, and then you have the coarse fibers surrounding the neck. Then you have the middle piece. The middle piece has the core of the coarse fibers, and then there are microtubules which are going to surround the coarse fibers. And around the microtubules, which is called the exoneme complex. So the microtubules which is surrounding the coarse fibers is called exoneme complex. And around the exoneme complex, there is a sheet of mitochondria. So within the neck, you have the center of core fibers. Then you have microtubules, which are 9 duplicates of the microtubules, which are called the exoneme complex. And surrounding the exoneme complex, there is a sheet of mitochondria. Then you have the principal piece. The principal piece has the core of the coarse fibers and the exoneme complex, but there is no mitochondrial sheet. There is only a fibrous sheet which is covering the principal piece. And the final part of the sperm is the end piece. So if we see it here, you will find that this is the head of the sperm, which contains mainly the nucleus, and on the top of it is this acrosomal cap. Can you make out this?
Yes.
This is the acrosomal cap. This acrosomal cap is the one which is going to secrete the acrosomal enzymes like hyaluronidase and others, which are important in digestion of glycoproteins surrounding the egg. Then you have this neck piece, which has centrioles and also the coarse fibers, which are going to form the foundation for the tail. In the tail, you include this middle piece and this principal piece, and finally you have the end piece. In the middle piece, you have the center of coarse fibers and these microtubules, which are called the exonemal complex, and surrounding these exonemal complex, you have the sheet of mitochondria. So this forms the middle piece of the sperm, and it provides, these mitochondria are important because they are providing the energy source for the sperm. If you look at the principal piece again has the center pair of microtubules and the outer pairs of the microtubules, which form the exonemal complex, and then surrounding it, rather than the mitochondrial sheet, now you have the fibrous sheet. So this is the difference between the middle piece and the principal piece of the sperm. So the principal piece is the longest segment of the tail and extends from the annulus to the end piece. The exoneme of the principal piece is continuous with that of the middle piece, and it is surrounded by the 7 outer dense fibers that are continuous with the other part of the middle piece, and in turn by the fibrous sheet. The end piece is 5 micrometer long and it's composed of the central exoneme surrounded by plasma lemma. So you would only have plasma covering the exodermal complex. There is no fibrous sheet in the end piece of the sperm. Okay, now let's talk a little bit on the Sertoli cells before we start to move towards the duct system. As we said, Sertoli cells are supporting cells. They are tall columnar cells with basal clear oval nucleus, and they contain cytoplasmic inclusions which are called the Charcot-Butcher inclusions, and we don't know the exact function of these inclusions. The cell cytoplasm is basically filled with the smooth endoplasmic reticulum, mitochondria, and well-developed Golgi apparatus. There are lateral extensions of these Sertoli cells, as we said, which divides the seminiferous tubule into a basal compartment and a luminal compartment. These extensions are going to connect the Sertoli cells with each other, forming the blood-testicular barrier, and we talked about it, why the blood-testicular barrier is important. So the function of the Sertoli cells is supporting the developing spermatogenic cells, establishes the blood-testis barrier. It phagocytoses of the cytoplasm, which is shed by the developing sperms, because if you see, initially they have the cytoplasm. As they are basically becoming more mature, they are going to shed their cytoplasm, which is going to be phagocytosed by the Sertoli cells. And it is important in manufacturing following substances. For example, androgen binding proteins, anti-Mullerian hormone, inhibin, and the testicular transferrin and fructose rich medium. Now among them, the most important ones are two of them. One is the androgen binding protein, which is secreted by the Sertoli cells. So what does the androgen binding protein do? Androgen binding protein is going to increase the concentration of the testosterone within the seminiferous tubule, because it is going to bind to the testosterone and keep it there. So you need higher concentration of testosterone within the seminiferous tubule, and it is basically achieved by the androgen binding protein, because it is going to bind with the testosterone and increase the concentration of the testosterone within the lumen of the seminiferous tubule. The other one is the inhibin, and inhibin is basically secreted under the action of the follicular stimulating hormone. And follicular stimulating hormone is going to secrete inhibin, and inhibin is important in terms of the stimulation of the testosterone. The other things which are there, which are secreted by the Sertoli cells, include the testicular transferrin, fructose rich medium. These are the other issues which are coming out from the Sertoli cells. Yes?
Why the Sertoli cells comes
so what you need to do is once the sperms are getting mature, they get attached to the apical surface of the Sertoli cell, and the Sertoli cell is taking the extra cytoplasm out of the sperm. This is a part of the maturation of the sperm, that the extra cytoplasm needs to be taken off.
So it takes it out to the sperm temperature.
Yes, it's a part of the maturation process. The epithelium of the seminiferous tubule, as we said, is surrounded by myoid cells. The spaces between the tubules contain connective tissue, blood vessels, and the interstitial cells of Leydig, which are important in secretion of the testosterone. Now, the blood testosterone levels are not sufficient to initiate and maintain spermatogenesis. And that's why the FSH induces the Sertoli cells to release a hormone which is called the androgen binding protein. And androgen binding protein helps in concentrating testosterone in the Sertoli cells. So this is an important function of the FSH. The FSH binds to Sertoli cells. It results in synthesis of the androgen binding protein, and this androgen binding protein is important in concentrating the testosterone within the seminiferous tubule. Release of LH is inhibited by the increased levels of testosterone and dihydrotestosterone, whereas release of FSH is inhibited by a hormone which is called the inhibin, which is produced by the Sertoli cells. So when you have enough amount of androgen binding proteins, the Sertoli cells are going to secrete inhibin, which is going to inhibit the secretion of the FSH from the pituitary gland. So that is also very, very important. Most of the cells which are under the action of the testosterone, they also have the enzyme which is called the 5-alpha reductase, which converts the testosterone into dihydrotestosterone, which is the most active form of the testosterone on these cells. So any cell which is going to be under the influence of testosterone also has this enzyme which is called the 5-alpha reductase, and this is important in converting the testosterone into the dihydrotestosterone. So this is just showing you that the luteinizing hormones act on the Leydig cells, and that results in the secretion of the testosterone, while the follicular stimulating hormone acts on the seminiferous tubule, and the acting on the ferrous tubule result in secretion of androgen binding protein, and androgen binding protein increases the concentration of testosterone in the seminiferous tubule. Once this secretion is higher or concentration of testosterone is high within the seminiferous tubule, the Sertoli cells also secrete inhibin, which actually inhibits the secretion of the FSH. So now we have done the testes, and we are basically talking. We are going to go from the seminiferous tubule to the intratesticular ducts, and then the extratesticular ducts system. So the first part of the duct system, we are going to talk about the intratesticular genital ducts, and these include the tubuli recti and the retitestis. So the terminal part of the seminiferous tubule is going to become straight, and as it is going to become straight, they are called straight tubules, or they are called the tubuli recti. So tubuli recti means straight tubules. These are the terminal portions of the seminiferous tubule. Now these terminal portions of the seminiferous tubules, they deliver the spermatozoa from the seminiferous tubule to the retitestis. They do not have the seminiferous tubules have two types of cells. They had the spermatogenic series and they had the Sertoli cells. The straight tubules will, in the initial part, would include the Sertoli cells, and in the later part, they would include simple cuboidal cells. So what you would have in the earlier part of the straight tubules is the Sertoli cells, and in the later part of the straight tubules, you would have the simple cuboidal cells which have a short, sturdy microvilli, and most of them have a single flagellum. So the straight tubules are formed in the initial part they are formed of the Sertoli cells, and these later half of these straight tubules would include cuboidal cells which have one flagellum or short, sturdy microvilli. If we go to the retitestis, which is basically a union or meshwork of tubules or meshwork of tubes, this is mainly would consist of simple cuboidal epithelium, and they would have numerous short microvilli with a single flagellum. So it would resemble the later half of the straight tubules. It would include simple cuboidal epithelium with numerous microvilli and with one single flagellum. Immature spermatozoa pass from the straight tubules into the retitestis, and from the retitestis they are going into these efferent duct tubes, and there are about 10 to 20 of these short efferent duct tubes that drains the retitestis into the head of the epididymis. The epithelium here consists of non-ciliated cuboidal epithelium or ciliated columnar epithelium. So there are two types of epithelium here. There are tall cells, columnar cells, which are ciliated, and there are short cells or cuboidal cells which are non-ciliated. The cuboidal cells have more of the microvilli appearance because they are going to absorb the fluid which is coming from the seminiferous tubules. So you have two types of cells in the efferent duct tubes. You have tall cells with cilia, and you have short cuboidal cells with microvilli. The function of the ciliated cells is to move the sperms into the epididymis. The function of the short cells with microvilli is to absorb most of the fluid which is coming out from the seminiferous tubule. Epithelium sits on a basal lamina that separates it from the loose connective tissue, and the connective tissue is surrounded by a circularly arranged smooth muscle fiber. So in the efferent duct tubes, you have the epithelia which has short and long tall cells, either ciliated or non-ciliated. We have talked about their function. Then you have the basal lamina. The basal lamina is covered outside by loose connective tissue, and outside the loose connective tissue you have a layer of smooth muscle fibers. So this is the first place after the seminiferous tubule that you start to see the smooth muscle fibers which are surrounding the loose connective tissue. Yes? Yes, they would contract and push the sperms, because sperms still do not have any motility. They would acquire the motility when they would reach the epididymis. Now we are coming to the extratesticular genital ducts, and within the extratesticular genital ducts we are going to talk about epididymis, we are going to talk about the ductus deferens, and we are going to talk about the ejaculatory duct. The first one is the epididymis, and epididymis, you know that it's a very long tube which is coiled. So it is about 4 to 6 meters long, but it is highly coiled. It has a head, it has a body, and it has a tail. There are several things which are happening here. One is the maturation of the sperm is happening, so it would require, it would get through a process of decapacitation, and then it would also acquire motility. So there are two things which are going to happen within the epididymis. One is the process of decapacitation, and the other is the acquiring motility. So and then in the tail of the epididymis, the sperms are going to be stored. So they are going to be stored for for weeks before they can be ejaculated, and they can be stored there. So the function of epididymis includes decapacitation, acquiring motility, and then storage is also there. Highly convoluted tubule consists of head, body, and tail. The lumen of the mucosa of the epididymis is lined by pseudostratified epithelium composed of short basal cells with round nuclei functioning as the stem cells, and the tall principal cells with basally located oval nuclei and stereocilia. So they have two types of cells which you are going to see. The basal cells, which are the stem cells, and they are actually producing the new cells. And then you have the columnar cells, which are called the tall principal cells, and they have the basal nuclei and stereocilia. Stereocilia are mainly long microvilli, and these long microvilli are important in absorption of fluid. They also secrete glycophosphocholine and glycoprotein, that inhibits the spermatozoa's capacitation. That means these glycoprotein and glycophosphoproline are basically laid over the top of the sperms, and that's why the sperms are not capacitated or decapacitated. Once they will reach the female genital tract, the female genital tract will take off these glycoprotein, and then sperm will become capacitated, and then it would be able to fertilize and move on. So the process of decapacitation is happening within the epididymis. The other thing which is going to happen within the epididymis is there would be a calcium influx into the sperms, which is going to result in them to acquire motility, because calcium influx will lead to induction of the phosphokinase and phosphatases, and these phosphokinases and phosphatases are important for motility of the sperm. So during the stay of the sperms in the epididymis, they would have a calcium influx which will induce the protein kinases and phosphatases, and that will result in the motility of the sperm. The epithelium is separated from the underlying connective tissue by the basal lamina, and then there are circularly arranged smooth muscle fibers which surround the connective tissue. Peristaltic contraction of this layer helps to conduct the spermatozoa to the ductus deferens. You would see that initially you would have a thin layer of the smooth muscle fibers in the early part or the head of the epididymis. In the middle part, you would have much more, several layers of the smooth muscle fibers. As we go towards the tail, you would have three distinct smooth muscle fiber layers in the epididymis, resembling that of the vas deferens. So, in the head, you have one single layer of the smooth muscle fibers. In the middle piece, you would start to have more layers, and as you go towards the tail, the smooth muscle fibers would be distinctly three layers, two longitudinal and one circular, similar to resembling the vas deferens. So epithelium is pseudostratified with tall columnar and basal cells. Principal cells are columnar. Basal cells are the stem cells or shoulder cells. They are going to have the stereocilia as a surface projection, and then they are going to sit on the basal lamina. Basal lamina is going to be separated by connective tissue, and outer to the connective tissue there is smooth muscle fibers. Smooth muscle fibers in the head, there would be one layer of the smooth muscle fiber, and as you go towards the tail, you would have multiple layers of these smooth muscle fibers, which would look like similar to the vas deferens. Yes. Yeah. So what I'm saying is that the epididymis, the epithelium, if you see here, is pseudo-stratified columnar epithelium, and it looks pseudo-stratified because you would have tall columnar cells, which are the principal cells, and you have these basal cells, which are the stem cells in the epithelium. So the nuclei are going to look up and down because you have these tall columnar cells and then you have these basal cells. So the epithelium looks like pseudo-stratified. The surface, the surface specialization is the stereocilia here, and outer to the epithelium there is a basal lamina. Basal lamina is surrounded by smooth muscle fibers. The connective tissue is surrounded by the smooth muscle fibers. In the head part piece, you have one layer of the smooth muscle fibers similar to the efferent ductus, and as you go towards the tail of the epididymis, you would see the multiple layers of the smooth muscle fibers similar to the vas deferens. So, highly coiled ducts are epididymis section here, which you are seeing. The wall is made up of pseudostratified columnar epithelium surrounded by the connective tissue and the smooth muscle. And you can see the two type of cells here. One is the principal cell, the other is the basal cell, and the surface, specialization is here is the long microvilli, which are called the stereocilia. No, from the tall columnar cells. Yeah, principal cells. The basal cells are not coming to the lumen. They are basically present at the basement membrane. So they are lying on the basal lamina, the basal cells. They are stem cells. They are producing more cells. So they are not the ones which are coming to the lumen. The main cells are the tall columnar cells are principal cells.
Basal cells are stem cells, yes.
Yes, and principal cells are columnar cells.
So they can make principal cells.
Yes, yes, yes. Next, we are looking at the vas deferens. Now, vas deferens is a highly muscular tube. It starts from the tail of the epididymis, and it passes over the back of the testes. Then it passes through the external inguinal ring, through the internal inguinal ring, and then enters into the abdomen, and then goes back towards the bladder, joins the seminal vesicles, and opens into the urethra with the ejaculatory duct. So, the vas deferens is a long muscular tube. Now, each ductus deferens has a thick-walled muscular tube with a small irregular lumen. So, what you are seeing is a small irregular tube, irregular lumen, and then you have a very muscular type of tube which you see here. So, you have the mucosa, and then you have the inner longitudinal layer, then you have the circular layer, and then you have the outer longitudinal layer. So you have three smooth muscles there. You have the mucosa, then the three muscular layers which you are seeing. The inner circular, the inner longitudinal, then middle circular, and then outer longitudinal muscular layer. The mucosa, similar to the what you saw in the epididymis, would be the pseudostratified columnar epithelium. There would be principal cells, and there would be shorter cells with stereocilia and a lamina propria. There would be thick outer wall which is formed by the smooth muscles, three layers: inner longitudinal, middle circular, and outer longitudinal. And then the smooth muscle layer is invested by a thin layer of the fibroelastic connective tissue. So there is a thin layer of fibroelastic connective tissue out. Then you have the longitudinal layer of the smooth muscle, circular layer. Then you have the inner longitudinal layer, and the mucosa is pseudostratified columnar epithelium with principal cells and shorter cells. Surface specialization also here is stereocilia. Yes, go ahead. Lamina propria is the connective tissue part of the mucosa. So below the epithelium, there would be some lamina propria, which includes some connective tissue and blood vessel. Okay? It will not have smooth muscles. Below the lamina propria, you would start to have the smooth muscles. Okay. So now we are going to talk about some, the seminal vesicles. We have to talk about the ejaculatory ducts. So the dilated terminal part of the vas deferens is called the ampulla. And ampulla, as it approaches the prostate gland, it is joined by the seminal vesicles. The continuation of the ampulla with the seminal vesicle is called the ejaculatory ducts. The ampulla of the ductus deferens join the ejaculatory ducts, and they are going to open into the prostatic urethra at colliculus seminolaris. Is a short straight tubule. Lumen is lined by simple columnar epithelium, and the subepithelium, the connective tissue, is folded, and it has no smooth muscle. So in the ejaculatory ducts, you have simple epithelium, simple columnar epithelium. You have the subepithelial connective tissue which is folded, and it has no smooth muscle. So in contrast to vas deferens, where you have three layers of the smooth muscle and your epithelium was pseudostratified with stereocilia, in the ejaculatory ducts you have the simple columnar epithelium, connective tissue is folded, and then there is no smooth muscles in the wall of the ejaculatory ducts. Okay, we give you 5 minutes break before we start the accessory genital glands, which we are going to talk about next are the seminal vesicles. We are going to talk about the prostate, and then the vulvourethral glands, and finally we are going to talk about the penis. So the seminal vesicles are about 15 centimeter long, highly tubular structures. They are located posterior aspect of the neck of the bladder and the prostate gland, and they join the ampulla of the ductus deferens just above the prostate gland. The mucosa is highly convoluted. So the mucosa of the seminal vesicle is not straight. It is basically highly convoluted. Because it is highly convoluted, that's why it looks like a tubular gland, a highly convoluted tubular gland. But it's just the mucosa which is highly convoluted. There are no glands there. It's the epithelium there is pseudo-stratified columnar epithelium, short basal cells and low columnar cells. There is subepithelial fibroelastic connective tissue, which is surrounded by inner circular and outer longitudinal smooth muscle layer. So what you have is a mucosa which is highly convoluted, and then you have a subepithelial connective tissue layer which is surrounded by a circular muscle layer and outer longitudinal muscle cord. The smooth muscle is surrounded by the fibroelastic connective tissue again, and this gland is going to produce viscous amount of yellow fructose-rich secretion. And so it is the major source of the nutrition to these sperms, because it is going to provide fructose-rich fluid which is yellow in color, and it is yellow because it has a pigment in it which is called the lipochrome pigment, and that gives the yellowish coloration to the seminal vesicle fluid. The other thing which you should know is that even though the prostate was called prostate because the prostaglandins were first found in prostate, but the most part of the prostaglandins are basically coming from the seminal vesicles. So most of the seminal vesicle fluid is very rich in prostaglandins. It is rich in the fructose, and it has a yellowish coloration because a pigment which is there, which is called the lipochrome pigment. So if you see here, the epithelium is pseudo-stratified columnar, and it is because it is so tortuous, it is going to, the epithelium is sent into convolutions. It looks like a tubular glandular structure. And then you have the muscle layer, which include the inner circular and outer longitudinal layer, which is present in the outside the connective tissue layer. And then over outside there is another connective tissue layer, which is outer to the muscular layer of the seminal vesicles. Next, we are going to talk about a very important gland, which is the prostate gland. It is the largest accessory gland which is pierced by the urethra as well as by the ejaculatory ducts. So the prostatic part of the urethra is also passing through the prostate, and the ejaculatory ducts are also piercing through the prostate. The prostate has a capsule, a slender capsule is composed of richly vascularized, dense, irregular connective tissue with smooth muscle fibers. The connective tissue stroma of the gland is derived mainly from the capsule. In addition, there are about 30 to 50 compound tubulo-alveolar glands inside the prostate. So you have a capsular stroma, and there is a fibromuscular stroma which is derived from the capsule of the prostate gland. And within the gland, there are 30 to 50 compound tubulo-alveolar glands. These glands are divided into 3 zones. The zone which is around the urethra is called the mucosal glands. Then you have the intermediate glands, which are basically present, outside the mucosal zone. And then you have the largest glands, which are called the peripheral glands, which are on the outermost zone. So you have 30 to 50 tubuloalveolar glands divided into 3 zones. The ones which are next to the urethra are mucosal glands. Then you have the intermediate glands, and then you have, or intermediate glands are sometimes called submucosal glands. And then you have the peripheral glands, which are the largest glands of the prostate. So they are arranged in 3 discrete zones, these tubuloalveolar glands. Mucosal, which are around the urethra. Then you have the submucosal or the intermediate glands, and the vast majority of the larger glands are present in the peripheral zone of the prostate. Between these glands, there is a rich fibromuscular type of stroma. So you have glands, and in between you have the fibromuscular type of stroma. The lumen of these fibromuscular glands will contain the prostatic concretions, and these concretions are called the corpora amylaceae. So corpora amylaceae are the prostatic secretions which become thickened, and they are present within the lumen of these glands, and they are called the corpora amylaceae. This is again showing you the distribution of the glands, and if you look at it, you would see that this is the prostatic urethra, this is the fibromuscular stroma, and these are the glands. So you can see these are the compound tubuloalveolar gland. In between you have the fibromuscular stroma. This is the prostatic urethra. If you see a more higher magnification picture, this is the epithelium of the compound tubuloalveolar glands, and this is simple to pseudo-stratified column. Some parts of these epithelium of the tubuloalveolar glands would have simple columnar epithelium, some would have the pseudo-stratified columnar epithelium. So the epithelium would be from simple to the pseudo-stratified columnar epithelium, and you would see the fibromuscular stroma, which is on the outer side. So this is the fibromuscular stroma. This is a higher magnification picture of the prostate, and within the lumen of the tubuloalveolar glands, you would see the concretions which are called the corpora amylaceae. The secretions of the prostatic gland are white, they are rich in lipid, they contain proteolytic enzymes, including acid phosphatase, fibrolysin, and citric acid. Fibrolysin is important because it is going to lyse the fibrin within the semen and making it liquefied. The acid phosphatase is also an important enzyme which is important in metastatic prostatic disease, when you would have high levels of acid phosphatase in metastatic prostatic cancer. The other important marker which comes out from the prostate gland is the prostate specific antigen. Prostate specific antigen is a tumor marker specific for prostate. It's prostate specific rather than cancer specific. So in normal prostate, you would have secretion of the prostate specific antigen within the lumen of the prostatic gland. But when you would have inflammation of the prostate or neoplasm of the prostate, this prostate specific antigen would get out from the epithelium and will get into the blood circulation. So if you have higher levels of prostate specific antigen, more than 4 nanograms per microliter, you start to think about the prostatic disease. So it could be because of benign prostatic hyperplasia, it could be because of prostatitis, it could be because of the cancer of the prostate gland. So it's not very cancer specific, but it is much more prostate specific. Now we know that prostate specific antigen also is secreted by other tissues like breast and liver. So initially we thought that prostate specific antigen is specific to prostate, but now we know that it is also secreted by other tissues, but in a very small amount. So, but still, for prostate specific antigen is a gold standard for identifying the prostate cancer. especially if you have higher levels than 10 nanograms per microliter, then it is very, very sensitive to detect the prostate cancer. The formation and synthesis of the secretion of the prostate gland are under the control of the dihydrotestosterone, and that's why when we have the prostatic hyperplasia, when your prostatic glands are increase in size or a hypertrophy under the action of the dihydrotestosterone, you give drugs which are going to block the conversion of the testosterone into dihydrotestosterone. So one of the drugs which is given to patients with benign prostatic hyperplasia is 5-alpha reductase inhibitor, so that you do not convert the testosterone to dihydrotestosterone, and that will result in decrease in the size of the glands in the prostate gland, and that will also will help in relieving the obstruction to the urinary tract, because once there is more glandular, especially the mucosal part of the glandular prostatic gland, if it increases in size, it is going to compress the prostatic urethra, which will result in obstruction of the urine. So in old age, as the prostate gland increases in size, it can obstruct the urethra, causing the urinary obstruction. So those people are usually given these drugs, which are the 5-alpha reductase inhibitors, and they stop the conversion of the testosterone to dihydrotestosterone. And because the glands are under the action of the dihydrotestosterone, once you give the inhibitor, it will result in decrease in the size of the gland and their secretion. Yes.
So I understand that prostatic gland hypertrophy is
you would have high levels of testosterone, then it would convert into dihydrotestosterone. So it will not become low. If you have high levels, then you would have high levels of dihydrotestosterone also, because you have 5-alpha reductase, which is converting it into the dihydrotestosterone. Yes. Yes.
In the reference book, it says that benign hyperplasia happens in the central zone.
Yes.
But what we took is it happens in the transitional zone.
No, I'm not saying it. What you're saying?
The benign prostatic hyperplasia.
Yes.
Is specific to which zone?
Yeah, it is going to be, the transitional and mucosal zones are the ones which are the ones involved in it, because they are closest to the urethra. The peripheral zone is mainly involved in cancers. Okay. Okay. The bulbourethral glands. The reason why it might have been written in the transitional zone, because major part of the glands are present in the intermediate and peripheral zone. There is very small amount of glands which are present in the mucosal zone. So even if they are going to enlarge, they are not going to be that many to compress the urethra. The bulbourethral glands are paired small glands, about 3 to 5 millimeter diameter, located at the root of the penis and just at the beginning of the membranous part of the urethra. So you can see it here. They are present at the root of the penis and just at the beginning of the membranous part of the urethra. So these are the bulbourethral glands. Their capsule contains fibroblasts, smooth muscles and skeletal muscles. The capsule sends septors to divide the gland into lobules, and the epithelium here consists of the compound tubuloalveolar glands and has simple cuboidal and simple columnar epithelium. The secretion is a thick, slippery fluid that lubricates the urethra. So the secretions which are coming from the bulbourethral glands are mainly the lubrication secretion. So before ejaculation, the secretion which comes out from the penis is mainly the secretion which is coming out from the bulbourethral gland, and these are mainly lubricative, slippery secretions. Finally, we are going to talk about the penis. It is composed of 3 columns of the erectile tissue, each enclosed by its own dense fibrous connective tissue capsule which is called the tunica albuginea. So there are two corpora cavernosa and there is one corpus spongiosum, and each of these three erectile tissues are covered by their own tunica albuginea. Two of the columns of the erectile tissue are called the corpora cavernosa and are positioned dorsally. Their tunica albuginea are discontinuous in places permitting communication between their erectile tissue. The third column of the erectile tissue is the corpus spongiosum, which is here, and it is positioned ventrally and it houses the penile part of the urethra. Corpus spongiosum ends distally in a large bulbous portion which is called the glans penis. So spongiosum is going to end up here, which is called the glans penis. Now if you see these corpora, these erectile tissue, you would see that within these erectile tissue there are vascular spaces. And these vascular spaces are lined by smooth muscles. Okay? So what happens is that when there is parasympathetic stimulation, these smooth muscles of the vascular spaces are going to relax and they are going to dilate. As they are going to dilate, these vascular spaces will be filled with blood. As they are going to expand, the veins are located outside outside these vascular spaces in the tunica albuginea. So as these erectile spaces are going to enlarge, they are going to compress the veins. So these dorsal vein of penis and other veins which are present on the outer part of the erectile tissue, they are going to be compressed by the tunica albuginea. So the venous drainage is obstructed. This will result in more engorgement of these vascular spaces, and as a result there is erection. Now on the other hand, when you would have ejaculation, there would be sympathetic stimulation which is going to contract these smooth muscle fibers. And as it is going to contract these smooth muscle fibers, there will be constriction of the blood vessels which are filling these erectile tissues. So the vascular spaces, the blood will stop going into them, the pressure would decrease, and as a result there would be drainage through the venous system, and that results in loss of erection. Now, for the parasympathetic innervation to contract these smooth muscle fibers to relax these smooth muscle fibers in the erectile, the vascular spaces here, you need a neurotransmitter which is acetylcholine. So parasympathetic nerves are going to release the acetylcholine. Acetylcholine is in turn going to result in secretion of the nitrous oxide from the smooth muscles, and the nitrous oxide is going to result in increase in the cyclic GMP, and that results in the relaxation of the smooth muscle fibers. And that's why when you have erectile dysfunction and you are given these drugs which are which helps in erection, for example the Viagra, which is commonly used, sildenafil is basically going to increase the cyclic GMP levels. So if you do not have the parasympathetic innervation to these smooth muscles, then even if you give Viagra, it is not going to help, because Viagra is going to increase the cyclic GMP levels because it is going to induce the nitrous oxide. The nitrous oxide is going to induce the cyclic GMP, which results in the relaxation of the smooth muscles and increase of the blood which is coming into the vascular spaces. So the other important thing is that if there is prolonged erection for more than half an hour or more than 2-3 hours, it is going to damage the parasympathetic nerves which are supplying the erectile tissue. So if somebody comes with prolonged erection for 4-5 hours, and it is going to permanently damage the parasympathetic nerves which are supplying the smooth muscles, And so if it happens, then there would be a permanent erectile dysfunction. That's why if you have, if somebody has erection for, for several hours, it's a medical emergency and you need to decompress the erectile tissue by taking the blood out from the corpora cavernosum and other places so that the erection goes down, because prolonged erection is going to damage the parasympathetic nerves, and then after that, even if you give Viagra, it is not going to work because there are no parasympathetic nerves left to secrete acetylcholine, which is going to result in secretion of nitrous oxide. Nitrous oxide is important in increasing cyclic GMP, and cyclic GMP is the one which actually relaxes the smooth muscles and increases the spaces of these vascular spaces. Thank you very much. We'll stop here.